everyone. Good to see you all. Okay, so let me make sure I got things covered for Thursday. Recitations on the usual schedule, review-ish. Reese and Ben ready to answer any questions you have on material from the first 5 chapters. They're going to have in their back pockets sample problems if you run out of time. Don't read anything into those sample problems. Office hours as usual. Help room. I realize I haven't reminded you of this for a while, but there is a help room in the department, open every weekday afternoon, roughly from 1 until 7, I think. It's kind of right up there, room 413, so another source of help. In terms of prepping, hopefully all of you have seen the sample exam. Reminders of things from last week. There are going to be 3 problems on the test. I've already talked about what I view as the kind of key topics we've covered. 2-dot level difficulty in general. If you look at the back of the textbook, and this is, as I talked about last week, not terribly well correlated with what Mastering Physics thinks the difficulty of problems are. 2-dot problems are kind of my goal, mastery of 2-dot problems. So that's the target. In terms of prep, hopefully you're all well on the way with this, but just some reminders. Reading the textbook is by and large a waste of time. So aside from doing it once when you first go through material, when it's useful, and possibly one more time on some slightly subtle things, which I mentioned I think in the context of Newton's laws. Reading the textbook beyond that is a waste of time. You're much better off working or spending your attention solving problems. So previous homework problems, you know there's additional problems posted on Mastering. So that's kind of, I guess the other thing I would mention are the in-chapter problems in the textbook. Again, generally pretty good. Don't look at the solutions until you've given it the best bet, the best shot. So those of you who've been reading your email for the past hour or so will have seen a notice about if you'd like a left-handed seat, send me an email before noon today. There should be a decent amount of space in here for the test, but as you see, there are places where if you're incorrectly seated and you're left-handed, you may have some difficulty. So let me know about that by noon. Calculator, any type. Bring a pen. Somebody asked me about this. I kind of would like you to write your solutions in pen. The reason for that is we've had, unfortunately, incidents in the past where people have written in pencil, and we'll talk about after the test the possibility to request a regrade if you feel that your test was incorrectly graded. We've had issues with people writing in pencil, which you can imagine I'm not going to talk about. So I would like you to write in pen. I know that's not your preferred thing for many of you, but by and large I think it's the best way to go in the test. Okay, I'm going to stop there and take questions on anything prepping for the test on Thursday. Yeah?
Just a second time, when are the office hours again?
Tuesday 3 to 4, Wednesday 3 to 5.
Can you do a work with pencil and write the answer to that?
I'd much rather you did everything in pen. It's just, I mean, the work is, that's something else I should mention, partial credit, very much emphasized in grading. So write as much as you can. Somebody wrote on Piazza last night, I think, what if I'm running out of time? My response to the viewer following Piazza will be write down as much pertinent information, and then when you have time, go back and work it. But again, partial credit's going to get you credit. So if you know things and you're out of time, write them down. So I still very much prefer pen. At the end of the day, there's usually a little bit of leniency, but I know you like to erase stuff and write again, but if you can get in the habit of simply if you write something that you don't like, after you've looked at it, just cross it out and write below. Is by far the preferred way. Yes.
Will we be expected to do the multifunction calculator, or can we bring a graphic one?
Multifunction versus graphing. Okay. My statement has always been you can use any type of calculator, and I think I still hold by that. I would like you, in the cases where you're solving equations, you need to at least, I mean, ideally you're going to solve it fully on paper. But generally I'll try and avoid problems where there's complicated calculational work to be done. So I stick by my any calculator statement. Make sure you are writing down any equations you're solving, you're writing down the equations you're solving before you put them in a calculator. I will ask the graders to be pretty understanding about just making sure you've got equations. Then if you solve them with some calculator, by and large that's fine, but you need to write down the equations kind of correctly. I know I didn't fully answer your question.
It's just like an addition, so for example, if you had a quadratic equation that you want to solve on the page, you can just plug that into your calculator.
Yeah, so again, I want you to write down the equation, the quadratic equation, and then just say, solving on my calculator, here are the roots of my quadratic. Yes. Yeah.
So since we're writing our response, do you allow it out, or do you want us to just cross it out?
I'd much prefer you just cross it out. And in practice, there tends to be a little bit of leniency here, but I think it's good to aim on writing everything in pen, crossing out, writing again. And you can imagine why that's. Chapter 5, chapters 1 through 5, inclusive, everything in those chapters, nothing beyond. Yeah.
Will we be able to use graphic?
So you'll use, this may be your first Columbia exam for many of you, you'll have Columbia exam booklets, that kind of blue-colored booklets. You should just put all your scratch work in there. If you want to do some stuff at the back, that's fine, but we will not collect loose pieces of paper, for example, so everything should be in those books. Yeah.
Will those notes be provided for us here?
Yeah. Books provided, formula sheet part of the exam, bring your calculator, and I think that's about it. All right, good. So keep in mind all of that. Okay, let's pick up back again. Remember last Thursday we started introducing the idea of work and really slightly more specifically mechanical work. So how we can define what we've now determined can be numerically expressed in this way. So it's the scalar product of a force and a displacement, and we're integrating it over some path length. So that by and large gives us a pretty general expression for work done. It's a scalar quantity, we talked about units, SI units or joules. So that's kind of where we ended up at the end of Thursday's class. Now, of course, you're very used to situations now where there are multiple forces acting, perhaps on some objects. And so if we're asking the question how much work is done, where we've got multiple forces, there are a couple of ways we can approach this. We can look at each force independently, separately, figure out the work done by that force with this prescription, and then add up the scalar quantities at the end to get the net work done. Okay? So again, with multiple forces, we can do this individually and do the summation. Or the other approach, of course, is to do the summation here, which is to say to find the net force by simply looking at the distinct forces, plugging in the net force here, and then calculating the work. Okay? So the question is simply, do I do the summation on this side, find the net force first, then calculate the work, or do I calculate the work by each force and then do the summation on this side? Of course, they're totally equivalent. So it's up to you which way you do it, but just keep in mind we will be using superposition or that sounds a little bit odd to me when I'm talking about a scalar quantity. Let me just call this summation. If multiple forces. Okay, and I talked about some sort of particular cases where there might even be work done by a particular force when the object is moving kind of in the opposite direction, in the opposite hemisphere is how I described it last Thursday. That's entirely possible if we've got multiple forces at work, so just keep that in mind. And since work is a scalar, of course it is signed, S-I-G-N-E-D, so you need to worry about positives and negatives, and again, if there are multiple forces at work, you need to take account of those signs correctly, okay? So I think all of that is stuff that you're pretty comfortable with. I'm not going to push it too much further. One thing we also saw in our definition of work last week was something we're going to elevate to the level of a kind of principle, which is the relationship between work done and change in kinetic energy. So once this thing is up and running, I'm going to slightly lower the amplification levels since it seems to be getting close to giving us some feedback. Okay, let's see how that goes. Okay, so let me write this up as a sort of principle now. So the so-called network kinetic energy theorem. There it is, pretty straightforward. So, that, hopefully we're in better shape now. So, maybe being a little bit more expansive here. We are talking in classical regime here, so nothing relativistic until the end of semester. Kinetic energy is just half mv squared. So the change in kinetic energy from some initial configuration to some final configuration can be associated with the net work done, okay? The net, again, keep in mind that embodies for us the possibility of multiple forces act here. So that's a useful thing to keep in mind. All right, so I'm going to kind of give a semi-rambling walk through a couple of examples here. They're pretty straightforward, but let me, for example, ask you to tell me if I take this piece of chalk and I lift it from being on the tabletop to up here. Okay, let's think about this. It starts off at rest. I apply some external force, raise it up to here, ends at rest. Okay, so what forces were acting on that piece of chalk during that operation? Okay, so two forces, gravity acting downwards, that's constant, and then my hand providing a force that's raising this thing up off the tabletop. In the first operation, raising this from here to here, is the work done by my hand positive or negative? Positive, right? Because the force is exerted at least in the same hemisphere as the direction of displacement. So I'm doing positive work. What about gravity during that first operation? Is gravity doing positive or negative work as I raise this thing up? Negative, okay? So pretty simple example, but tell some of you were thinking a little longer on that one than when you were thinking about the work done by my hand. Okay, flip things around and let this thing go. Or maybe I'll just drop it down here. And of course the signs of the work done flip. Okay, so there gravity does positive work, and to the extent that I'm applying a force here, which is barely true, but I am, you can imagine that I'm kind of holding it up in some sense. All right, so what about if I go from here to here and apply my network kinetic energy theorem? What can you tell me about the magnitude of the work done by my hand versus the work done by gravity in that operation? Yeah? Good. So they better be equal in magnitude. Of course, they're opposite in sign. Why must they be equal in magnitude? Because they start off and end up at the same velocity, namely 0 in this case. So since my kinetic energy doesn't change, the net work done must be 0. So the work done by gravity must be equal and opposite to the work done by my hand. Okay? So pretty simple, but there's possibilities for getting a little bit confused with these sorts of things. All right, fairly straightforward. Now I'm going to turn to a kind of new type of force that we haven't really explored yet, though most of you know about it. And it's a specific example where we've got a force that is variable. So this is going to be a spring force. And let's see, I don't have any good example. Maybe let's try this one. No, too stiff. Let's try this one. Also a little bit too stiff. Okay, maybe the best one we've got. Not great. Spring. I can sit this on the tabletop here. And it has what I'm going to describe as a relaxed length. So that's the length it likes to be right now. But of course, as you know with springs, I can attach things to the ends of them and either compress or stretch the spring. So if I compress this, you can't particularly tell, but there's a force that's pushing back on my hands. Okay, it wants to revert to its relaxed length. So in that sense, this force is exerting the spring is exerting a force that's pushing back against the displacement of the ends. Okay? Conversely, if I take this and I grab all of the ends and pull them apart, so I'm stretching rather than compressing it, again, you can't particularly see this, but you know it's true. There's now a force tending to pull this back together to its relaxed length. Okay? So this is about as simple of an example of a spring force as I can show you. And it has a couple of really interesting characteristics which turn out to be very prevalent in nature. Not that springs necessarily are prevalent in nature, but forces that behave in some approximation like springs are super prevalent in nature. So what are the characteristics? Well, first off, that, and again, you could kind of show this. In fact, maybe I can even show you this with a series of weights hanging on the end of springs, but I don't think I'm going to, if you understand what I'm after. There are a couple of features that are interesting. First off, force seems to be proportional to, let me call it, the displacement from the relaxed position or relaxed length. So again, you can't particularly see this, but you kind of know it's true. If you stretch a spring more, the force that's pulling back is stronger and less commonly experienced, but equally true. If you compress the spring, the more you compress it, the more it's pushing back. So it turns out it's roughly proportional. Not always, this may be an approximation in some cases, and we're actually going to take the case where it does obey this behavior and call it Hooke's law. Okay? So, proportional to the displacement from a relaxed length. I'm going to make this even simpler and simply say that I'm going to set x equals 0 at maybe the point where this is at its relaxed endpoint, and use that as my reference point. So if you allow me to set x equals 0 at one end, I can in fact simply write this as f is proportional to x, where x is the absolute value from that chosen displacement. So just make sure that's clear. X equals 0 at the relaxed endpoint. Okay, so that turns out to be pretty common behavior for ideal springs and surprisingly common. The other feature of this I want to build into here has to do with the directionality. So I claimed that when I pull this thing apart, it's tending to pull backwards towards its restored length, and conversely, when I squash it, it's trying to push back towards its restored length. So how would I represent that simply in some mathematical way here? Yeah? Sure. Or a minus sign. So this is what's called a restoring force. It's tending to restore the object to its relaxed position. Notice I'm kind of avoiding using equilibrium because that can come around in different situations, but we're talking about restoring force towards the relaxed length in this case. So we've already learned two important things: the proportionality to displacement, the restoring nature, hence the negative sign. And as usual, the last step here is going to be to replace our proportionality with a constant and an equal sign. So we can write it like this. Okay, constant of proportionality. Not very imaginatively, we're going to call this the spring constant. There it is. This is Hooke's law, and again, some approximation, behaviors like this between objects are surprisingly common in nature. And in certain regimes, if we're looking at interatomic, intermolecular forces, in certain regimes, this holds true as well. You'll have heard me a few times over the past month already at this point, talking about this sort of mattress image that I have mentioned as a way to think about things at the atomic or molecular scale. And this is very much kind of embedded in that image, in the sense that you can imagine in certain regimes that the forces between neighboring atoms or molecules behaves very much like this. Okay, so that's why this mattress model has some relevance. So there it is. Hooke's law, aka idealized spring behavior. All right, so now we've got for the first time, I think, an explicit kind of non-constant force. Okay, clearly this depends on the amount of stretch. So if you think about a lot of the stuff we were doing earlier in the course, particularly constant acceleration and motion, we're immediately in a situation where that's not applicable because we don't have a constant force anymore. This is a case where there's no constant acceleration, so it's not a constant force, and so the acceleration is not constant. All right, fine. So let's come back and talk about this in the context of work, because now we've got a force that's a little bit different than ones we've seen before. But we can still go back and apply our definition of mechanical work done here. And a simple way to show this, just take that. So the work done is, as we had before, F dr, something like this. And so if I take my Hooke's law behavior here and simply make this minus kx, what you can show pretty straightforwardly by just putting this in and doing the integration is the following. So the work done, and I'm going to be pretty clear here, it's important, the work done by the spring itself, okay? So remember the example I had a few moments ago of my lifting a piece of chalk, and with gravity I'm applying an external force. Of course, when I stretch or compress the spring, I'm also applying an external force. And we have to be careful which object we're talking about doing the work, okay? And again, if they end up at zero velocity, beginning and end, we can expect that the work done by the spring force and by me as an external agent are equal and opposite. So keep in mind what you're talking about, the object doing the work, and in this case, if you plug in Chuck here for this particular force, what you will find is that this can be written as 1/2 k x1 squared minus 1/2 k x2 squared. Note the order, because there's a minus sign in here. What comes up with a positive sign is the initial position, initial displacement. What comes in with the minus sign is the final displacement, just because I'm integrating something which had a minus sign associated with it. So now we've got an expression, in this case, for the work done by a spring force as an object is moved on the end of that spring. Okay. So, as I said, a kind of slightly rambling exploration of work done by certain types of forces. I obviously haven't been totally exclusive here. We haven't gone over all of the forces we talked about before. There's no need. It's pretty straightforward. Mostly up until now we've been dealing with constant forces like the gravitational force we had that quick example with. The first time we're dealing with an explicit variable force, and again, it's straightforward to figure out what work done is. Any questions? Yeah?
Are you integrating From X to two.
Yeah, would be good if I'd written that down. Yep. Okay. So, just a side comment. Yeah.
So like R, that's the same as X, right?
Yeah, so this was a more generic definition that would allow us to be worrying about 3 dimensions, of course. But yes, in this case, dx, because I'm confining myself to being along the x-axis. So I'm going a little bit fast here, and that's why, because you're catching me on some details that I wasn't explicit about. Okay. Okay. A bit of a side note. Work as the area under a force versus, how do I want to write this? Delta x plot. Okay, that means force versus delta x, for example, force versus displacement. I think we talked about this idea previously. If, for example, I had force as a function of x and some displacement here, we've got a very simple prescription for figuring work done when we've got a well-behaved, by which I mean mathematically well-behaved force. We're only going to deal in this course with well-behaved functions, but I just want to extend this for 2 reasons. First off is to imagine a case where I had some force that had some crazy behavior. It's a little bit hard to imagine what this might be, but by crazy behavior, I mean it maybe has some just discontinuities, starts to become mathematically unwell-behaved. When I have things like this, it gets to be tricky to do an integral in the formal sense. But what I can do instead is associate the work done by some force as actually being equivalent to the area under a force versus displacement figure. So I can simply imagine what the work done under here is as being associated with the area under that curve, okay? And we've talked, I think, a little bit in the past about how doing an integral like this corresponds exactly to the area under a force versus displacement figure. And so you may once in a while, though I think I'll rarely give you any problems like this, be asked to read off some graphical information. So you're presented with some figure of force versus displacement. Maybe a problem asks something like, just by looking at the plot, calculate or tell me what the work done is. And what it's asking you to do is look at the area under that curve, possibly between some limits, so x1 and x2, for example. And I should make a footnote here, it's entirely possible that that area could be negative. What do I mean by negative? I simply mean that it's below the f=0 axis, okay? So again, that's just a reminder of the importance of keeping track of sign of work done, depending on whether the force and the displacement are in the same hemisphere or they're in the opposite hemisphere. So that's just a sidebar comment that we may sometimes be interested in trying to extract some of this information graphically, as opposed to doing the simple calculation. Okay, almost done on our definition of work, and then we're going to turn our attention to other types of energies. I want to mention the very much associated idea of power. So everything we've talked about so far has not mentioned time at all. There's certainly no inclusion of time in our definition of work done. It's simply the path integral of force dot displacement. So time isn't coming into it. But of course, you know from day-to-day experience that the rate at which work is done can be very important in many instances, and that's what we define as power. So the power, I'm simply going to define as really, let me do this, maybe as a derivative, it's the rate of doing work, okay? So that's going to be our instantaneous power. If we happen to care about average power, I can write an average, which might be simply the amount of work done over the time interval in which it is. So again, you're very familiar with these distinctions now.